Buenos dias. Hello, hello, hello. We're here to learn integration by parts. And you being second semester students of calculus will start to see that what it is that we're doing different types of integration techniques that make it more simple to solve these equations analytically. It's really, I call them tricks of the trade. Because if I have x times the sine of x, and I want to integrate that from 0 to pi dx, and I'm going to use integration by parts technique to solve it. So to begin with, I'd like to just derive the actual equation for the formula of integration parts. And that's done with the product rule. So I have two functions, f times g. When I take the derivative of it, it becomes f prime g plus f times g prime. Now, how I remember it is like you tickle the first guy f and you let the other guy rest, and then you let now the other guy rest and you tickle the other guy. So if I want to now get rid of this, I multiply both sides, let's say by d of x, and the differential, and now I want to get rid of this d. When you take the integral of a differential or derivative, you're going to get the function back. That's the fundamental theorem of calculus. That's a duality that exists. So when you integrate the derivative, you're going to get back the actual function f and g. These you don't much you can do about it because you don't know what it is that you have to integrate. However, if I take this guy right here, you see the one here with the f prime, and I get it algebraically by itself. That is, I subtract this guy from both sides, see, and then change the. I just put this on the left side, and then I have this side. You see, I subtracted that to over here. Then I just changed the order. So that is the formula for integration by parts. Do an example of x using x sin x dx using parts. So but let's see what that looks like first. So let's go over here, and then I'll share the screen, and then we have this. Now let me show you. Pull it out. Look at that. Notice how the amplitude in both directions is getting bigger and bigger. That's pretty cool, isn't it? For me, there's a nexus between mathematics and art, and I think it's the symmetry of things, which is a good mathematical property. So what I'm asking, though, is that as I zoom in, and this equals x times the sine of x, but what I'm asking is I'd like to know what the area on the curve, this curve, is from 0 to pi. So I know that's 0, but where it intersects here, you see that? Oops. Right, x is pi and y is 0. So I'm just going to find the area under this little hump here. Okay? So here I put it in this calculator, online calculator, y equals x sine of x. Right, now let's go back to that, and then here, let's go back to the whiteboard. Okay, now the tricks of the trade, the techniques of integration on this example is what should f be equal to the x, and g should be equal to sine of x, or in what way should we set it up so we can fill up this equation here, which is the integration by parts. Well, and if, by the way, if you get it wrong, you may actually make the problem more complicated. So the process is that as you go through this, you want it so that it ends up after you've done your integrations, that it's actually easier. So it's easier to finish. So let's see. So to make this work, I've tried the following. I let f equal to this x. But if f equals to that x, then the derivative of x is 1. Then I let g prime, that means the derivative of g with the sine of x. Okay? And then I wanted to, from that, derive g. Well, again, the fundamental calculus, because if you take an integral of the different derivative, and then I'm taking the integral of both sides of this, that's what I do up here. And it turns out that when you take the actual integral of the sine of x dx is equal to minus cosine of x. So we know what I'm doing is I'm assigning g prime to sine of x. So I've replaced g prime with sine of x dx. But we know that the integration of, the derivative of sine of x is cosine of x, but the integral of sine of x is minus cosine of x. Now we got it established. So now we had to use the fundamental theorem of calculus to get this last point g. Now we can start plugging in. This is the equation by parts. So I can see now what I'm going to do is this is f prime, you see? So f prime I said equals 1. Well, there's the 1. I put it in there. And then what's g? You have to look over here. We solved that. That's minus the cosine of x. And that is going to have to go from 0 to pi. And then you have dx. Now let's look at the next thing. It's equal. See the equal sign? Go over here. Now you have what? Well, let's have f again. What's f? Oh, it's x. There it is. And how about g? Oh, it's minus the cosine of x. So that's x times the cosine of x, evaluated from 0 to pi. And then finally, this last one here, we have minus the integral of f. Well, f is x. And g prime of the g prime of x, you see, is the sine of x. So this could look kind of familiar, because actually that's what I'm trying to solve for in this last bit. It is the integral of x. Here it is, see it? What I want to do to begin with. So what I'm going to do is evaluate these integrals. And it turns out that, of course, the integral of cosine of x, so we're going to take that's going to be sine of x, sorry, minus cosine of x. So there's the minus cosine of x. And when you integrate it, we're going to have the sine of x, because the integration of cosine of x is minus the sine of x times the minus you see up here. So that makes it a positive sine of x. And then it has to be evaluated from the upper and lower limit from 0 to pi. So that equals, now we go to the next part. We have, well, this is easy because it just needs to be plugged in. So we have x cosine of x, which we will be putting in these limits. But this guy, to integrate it, well, it's not that we want to, well, we're trying to integrate it. That's what we're trying to look for the answer for. So that goes from 0 to pi, and I just leave it alone. It's x sine x dx. That's what we want to solve. But I'd like to get this red thing by itself, you know. So I'm going to put the red thing on this side, and then I'll bring this thing. Let me show you what I mean, just so I don't skip this step for you. Let's see. So what I'm saying is that this is x cosine of x. All right, that's no problem. It's right here, and I don't have to do anything. But this integral, I'm going to move it to the other side, so I'm going to add. So now what we have is this becomes the sine of x, yeah, evaluated from 0 to pi. Then we have x cosine of x, which will be evaluated from 0 to pi. And now with this. Now I just want to get this by itself, and I want it positive. And then I want to get this one out. So what I mean to say is that we're going to have something like this. So I'll have, it looks just like this above here. We're going to take the upper limit and put it in here so that we have sine of pi. So that's 0. And at 0 itself, the sine is also 0. So all of this is 0. Big fat 0. And now, let's go to this one. Now, when you put that in, that's going to be minus pi times the cosine of pi. Now, the cosine of pi will be like this. So that it actually, when this is at pi, okay, so it looks something like this. It starts up like this. When that's at its height, that hits 0. And when that's at 0, it hits 1. Okay, so what I'm telling you is that for cosine, the cosine of pi is minus 1. And minus 1 times minus pi, right, is right here. And then the second part is to evaluate this at the lower limit. Well, 0 in there is 0 is now x, and cosine of 0. Well, the cosine of 0 is 1. See it up here, 1. But you're multiplying times 0. Doesn't matter. That's a big fat 0s right there. So now I'm gonna get this by itself by adding it to this side. See, and I already know that this thing is equal to minus 1 times pi plus 0. Right? This is already 0. All I'm doing is subtracting this. Adding this to the other side. When I do that, then I have minus pi cosine of pi. And pi minus pi times minus 1 plus 0 is just pi. And that's your answer. It turns out that the area under that curve is pi. That's okay. Thanks.